focused most of our attention in the last few lessons on trigonometric functions for acute angles, but we might be interested in evaluating trigonometric functions for any angle. So the question is, how can we do this? We've done most of our work inside of quadrant 1, and inside this quadrant both x and y happen to be positive numbers. Since our trigonometric functions are going to be defined by points that lie on the unit circle, we can note the following pattern for our quadrants. As we move over to quadrant 2, x becomes negative and y stays positive. As we move down into quadrant 3, both x and y are negative. And moving over into quadrant 4, we have that our x value is positive, but our y value is negative. So let's see if we can use this overall pattern to help us figure out where our trigonometric ratios are going to be positive and where they're going to be negative. So these properties that we saw on the last slide are going to help us develop what we call the cast rule. And the cast rule is used to remember where our trigonometric functions are positive and where they're negative, given a particular quadrant on the xy plane. Starting up here, since both the x and the y coordinates are positive, all of our three usual trigonometric functions are positive: sine, cosine, and tangent. So we might say something like all. As we move over to quadrant 2, notice that our x value here is negative, but our y value is positive. So we have that our sine function is always going to be positive in this particular quadrant. Moving down to the third quadrant, we have that the x value and the y value of our terminal points are going to be negative. This means sine is going to be negative, cosine is going to be negative, but our tangent function, which is the ratio of our two coordinates, is going to be positive. So down here in the third quadrant, tangent will be positive. And finally, in the fourth quadrant, where we have our x values as positive and y values as negative, our cosine ratio is always going to be positive. Thus, if we take the first letters from the phrases that we have written down, we get the cast rule for our trigonometric functions. So cosine is positive down here. All of our functions are positive here, sine is positive here, and tangent is positive here. So if you ever see me write something like this is because I'm going to apply the cast rule to the particular question that we're looking at. Let's use what we've learned on the previous two slides to find the 6 trigonometric ratios given an angle of theta equals negative pi by 3 radians. I'm going to begin here by drawing the right-hand side of our xy plane. And I'm going to put in two different angles. I'm going to put in the angle of positive 60 degrees, as well as the angle of negative 60 degrees. Next, we know that these two angles are going to intersect the unit circle somewhere. We happen to know the terminal point for the angle pi by 3, so let's put that in up here. We're going to call this point P, and we know that the terminal point up here is 1/2 and root 3 over 2. Now the idea to solve questions where we have angles like this that aren't in the first quadrant is to use this reference point, or this reference angle, to help us figure out what the point is down here. So once again, we're going to have a new point down here. Let's call it P1. And here our x-coordinate is going to be the same. However, we've gone downwards in the y direction. We could change square root of 3 over 2 to negative square root 3 over 2. And now we can use this relationship down here to figure out our 6 trigonometric ratios. So let's begin filling in values for our trigonometric ratios, starting with sine of negative pi by 3. Well, if we know this point down here, sine is going to be the y-coordinate of this point. So sine of negative pi by 3 is going to be negative square root 3 over 2. Cosine of negative pi by 3 is going to be the x-coordinate down here, or it's going to be 1/2. And tan of negative pi by 3 is going to be the y-coordinate divided by the x-coordinate. In this case, we're going to get negative square root of 3. Next up are our reciprocal trigonometric functions, beginning with cosecant. Cosecant is going to be 1 over sine, so we're going to get negative 2 over square root of 3. And if we rationalize the denominator here, we're going to get negative 2 times square root of 3 over 3. Next is secant. Secant is 1 over cos, and the ratio we get here is going to be 2 over 1. Finally, for cotangent of negative pi by 3, we can take our tangent ratio, which is negative root 3, and flip it to get negative 1 over root 3. And remember that we can rewrite this as root 3 over 3. Let's do one more example. We're going to find the trigonometric ratios given theta is equal to 5 pi by 6. So let's begin by drawing 5 pi by 6, and that's going to be this angle measure here. And I've also drawn in pi by 6, and that's this angle measure here. Now you might wonder here why I've also drawn in the angle measure of pi by 6. Well, that's because the reference angle for 5 pi by 6 is going to be pi by 6. So I know that's the one that I have to compare to when I'm going to look at my terminal points. I know that the terminal point for pi by 6 is going to be square root of 3 over 2, comma, 1 over 2. And so I can use this information to get the terminal point for 5 pi by 6. So here, only the x value is going to change. It's going to change to negative root 3 over 2 and 1 over 2 like this. So from here we can easily get at our three major trig functions. We know that the sine is going to be 1/2. We have cosine is negative square root 3 over 2. And tan is going to be negative 1 over root 3. Or if we rationalize the denominator, negative root 3 over 3. And now that we have our three major functions, we can go and get our reciprocal functions. Beginning with cosecant. Cosecant must be 2. Secant must be negative 2 over square root of 3. And if we rationalize the denominator here, we'll get negative 2 root 3 over 3. And our cotan of 5 pi over 6 must be negative square root 3. The work we've done on the last couple slides, while useful for us to evaluate the angles, might not be the fastest or most efficient way to do this. So we're going to combine the cast rule with reference angles to be able to evaluate a trig function at any angle that we call beta. The idea is, if we have the angle beta, we need to find the reference angle theta. After we have the reference angle, we can evaluate the trig function at our reference angle. And then our last step is to use the cast rule to determine whether or not our original expression needs to be positive or negative. So let's take a look at a few examples of how to do this particular procedure. Let's begin by trying to evaluate tan of negative 5 pi by 6. So how I generally tackle this question is I draw a little cast rule over here at the bottom, and I want to figure out in what quadrant negative 5 pi by 6 is. Well, since we have a negative radian measure, we're going to be going in a clockwise direction, beginning at our positive x-axis. So 6 pi by 6 is going to be this distance here. So I'm going to be going almost all the way to negative 6 pi by 6, but not quite. So we're going to be somewhere inside this quadrant here where tan is positive. Noting that we have a denominator of 6, we can use the reference angle of pi by 6 as well as the cast rule. So here I know that tan is going to be positive. Thus, it must be that tan of negative 5 pi by 6 is equal to tan of pi by 6. And then we simply just have to know our first quadrant. What is tan of pi by 6? Well, tan of pi by 6 is 1 over root 3, or root 3 over 3. Let's repeat the same procedure over here with sine of 11 pi by 3. Once again, I'll begin by drawing a little cast rule down here at the bottom and trying to determine where 11 pi by 3 is. Well, in this case, we're going to be opening in a positive direction, so we're going to be going counterclockwise. Starting here, we have 0, and opening up to 3 pi by 3, 6 pi by 3, 9 pi by 3, and back around to here would be 12 pi by 3. So I'm going to fall just short of 12 pi by 3. So I'm going to be down here in the fourth quadrant where cosine is positive. So that means that sine of 11 pi by 3, since its reference angle is pi by 3, should be equal to sine of pi by 3, but I have to change the sign to a negative sign. That's because sine is not positive down in this quadrant. Now we can go to our first quadrant that we know and evaluate sine of pi by 3. That is square root of 3 over 2, so our overall answer here must be negative root 3 over 2. In this last example, we know that cosine of theta is equal to 1/2, and that sine of theta is negative. What we'd like to do is find the value of theta. So let's begin by considering the cast rule. We would like to figure out in which quadrant our angle theta is going to be in. So let's first use the fact that sine is negative. That's going to remove these two quadrants because in these two quadrants we know that sine is positive. We also know that our ratio for cosine is positive, so that's going to cancel out this quadrant as well, because in that quadrant cosine would be negative. So there's only one possibility here for our quadrant that we're in. So let's go ahead and draw a triangle in here. And what we're after is this reference angle in here. Let's call that beta. We happen to know that cosine of theta is equal to 1/2, and that's going to tell us that the adjacent side over the hypotenuse is of the ratio 1 over 2. Or in other words, I can put a 1 here for the adjacent side of beta, and 2 here for the hypotenuse. Well, it looks like we have a 1, 2, square root 3 triangle, so the other side that's missing here is square root of 3. And from this particular diagram, we can then conclude that our reference angle of beta must be 60 degrees, or pi by 3 radians. Now it's not going to be true that the value of theta is equal to pi by 3. Pi by 3 just happens to be our reference angle for this particular quadrant that we're in. What we have to do is figure out the true value of theta. And our true value of theta is going to be between negative pi and positive pi. So that means we could use negative pi by 3 as our value of theta in this case. Alright, my little epsilons, stay positive.